So this is part 2 of our discussion on Morse functions. In this lecture, we are going to talk about the extension of the ideas that we have seen earlier about Morse functions to piecewise linear functions. Let's first answer the question, why piecewise linear functions? Scientific data often comes to us and is made available to us as samples rather than as analytic functions. So we are often given a domain and a scalar function which represents a scientific data, where the domain is represented by a mesh. In the language of this course, the domain is represented by a simplicial complex, which is a triangulation of the domain. The scalar function is not available in its analytic form or closed form. However, it is available as a sample at discrete points of the domain. The points on the domain where the function is sampled is essentially the vertices of the simplicial complex. And we use the simplest possible interpolation, namely linear interpolation, to extend the function to the interior of the cells or the simplices. So the question now is, how do we extend the Morse theoretic ideas that we have seen so far to piecewise linear functions? Let us start with an example in 1D. So a one-dimensional domain is a curve which could be represented or approximated by a piecewise linear curve. Let's look at a particular point on this piecewise linear approximation, namely a vertex. How is the neighborhood of this vertex defined? The answer here turns out to be easy. The adjacent vertices essentially constitute the neighborhood of this vertex. How do we classify this vertex as a critical point or not? That also turns out to be easy. So the vertex is a minimum if the neighbors are greater. So essentially the neighboring vertices have a function value greater than the vertex. If the neighbors are smaller, then the vertex is a maximum. If it is neither, then it is not a critical point. So how does this extend to 2D and in 3D? In order to even consider these extensions, we need a stronger notion or a more formal notion of neighborhood. We already know the building blocks of the simplicial complexes, namely the K-simplex. So let's start with that. We know that a 0 simplex is a vertex, a 1 simplex is an edge. I'll use labels here so we can talk about them. A 2 simplex is a triangle. And a 3 simplex is a tetrahedron, which I will not try to draw completely to avoid clutter. I'll just show you that that is a tetrahedron, A, B, C, D. We have already seen the notion of boundary. So in this lecture and in future lectures, I will restrict to addition modulo 2. So the boundary of the tetrahedron would be would constitute the triangle faces ABC, ABD, BCD, and so on. So we have already seen the notion of a face, but let me try to define that here. So let's consider a K simplex here. Let's say a 2 simplex ABC. We have already seen the notion of the boundary of this 2 simplex. So the boundary of this 2 simplex would be AB, which is the edge AB, that is my notation. Right? So again, you would notice that I have not written the subscript here because that's fairly obvious, but you know that that is 2 because we are talking about 2 simplices. So ABC is a triangle, is a 2 simplex. Its boundary is AB plus BC plus CA. Similarly, the boundary of AB is A plus B. We call tau a face of a simplex sigma, right, written in this way. So tau is a face, right? If it is a simplex that is defined as the convex hull of a subset of the vertices that define sigma. So let's use examples to understand this. The formal definitions are already in the notes. So AB is a simplex sigma. A is one of its faces because it is a simplex that is defined by a subset of the vertices that define AB. So similarly, A, the vertex A is also a face of the simplex ABC. If tau is a face of sigma, then we call sigma as a coface of tau. Right? So note that the term face refers to the English term phase as well, but extends to all lower dimensional phases. So if you consider the 2 simplex ABC, then its faces include the edges AB, BC, CA, and the vertices A, B, C. So when we look at this later, we will optionally include the empty set, which is also a simplex, kind of trivially. Right. So let's now move on to the notions of neighborhood of a vertex. So these notions work for all simplices, but we will focus on the notion of a neighborhood of a vertex because that's what we will need for this lecture. But the definitions that we are going to see here extend to neighborhoods of other simplices as well. So we will talk about the neighborhood and define the star and link. Let's consider a vertex V. Now we want to talk about its neighborhood. So we will restrict, for this example, we will consider a two-dimensional simplicial complex. So first I want to talk about the neighborhood of V in terms of what I call the star of V. The star of V consists of all the edges that are cofaces of V. So edges such as VV1, VV2, VV3, let's say VV4 and VV5, and other cofaces such as VV4, V5, VV3, V4, VV2, V3, VV1, V2 and VV1, V5. So the star is essentially the collection of cofaces of V. So note that this star need not be a simplicial complex. For example, the star contains the triangle V1, V2, but it does not include the edge V1, V2. So star of V need not be a simplicial complex. We could make it a simplicial complex by including all the faces, and we call that the closure of this star. Right? So the closure of the star is the star together with all the faces that are not included in the star. So this is the closure. So in this case, the closure is all the simplices that you see here in this picture. So note that the way we define cofaces, V is a coface of itself. So the star of V includes V. Right? So the star of V includes V. The next notion of neighborhood that I want to define is called the link. The link of V is essentially all those vertices and edges that are one hop away in this case. More formally, it is the difference between the closure and the star. Right? So the link of V in this case is the collection of all the simplices that are in the closure of the star, but not incident on V. So whatever I'm trying to draw here in black are those simplices that are in the closure of the star, but are not incident on V. So this is called the link of V. The link of V. Now that we have a way to describe the neighborhood of a vertex, we can further classify it based on a scalar function that is sampled at the vertices. So we can talk about the lower star and the lower link. what we will really need is the notion of lower link. So I'll talk about that. So we need a notion of a lower link, correspondingly something called an upper link, which is defined similarly. So let's just look at the lower link first. So the link of V here consists of all the vertices V1 through V5 and the edges V1, V2, V2, V3 and so on. Let's assume that some of these vertices have function value lower than that at V, right? So for example, f at V4 is less than f at V, and let's assume f at V3 is less than the function value at V, right? Let's assume that the function value at the other three vertices are greater than f at V. The lower link of V is a subset of the link of V that is defined by the vertices that belong to this set, right? So the collection of vertices which have function values lower than that of V. This constitutes the lower link. So in this case, V4 and V3 belong to the lower link, and all the edges that are defined by these, that are induced by these vertices, also belong to the lower link, right? So the lower link is essentially the set of all simplices in the link of V, right, such that the function value at, let me use the abuse notation, at sigma is less than f at V. What I mean f of sigma is that the function value at all the vertices that define this simplex sigma are less than f at V. This also means that the function at any interior point of sigma is also less than V, because we use linear interpolation. So if f at V4 is less than V and f at V3 is less than V, we know that all the function, if it is linearly interpolated along the edge V4, V3, then f along V4, V3 should also be less than V, right? So this is how we define the lower link. So similarly, we can define the lower star as well. I will not write this down. So the lower star essentially is the collection of all the simplices of the star where the function values are lower than that at V, right? So the upper star and the upper link are defined similarly, right? So the upper star, upper link are defined similarly. Okay. So what we would need in the future few slides is just the notion of lower link in order to classify critical points. So let's look at that. Let's again continue with the 2D simplicial complex. So I have a vertex here, V. I use blue to indicate lower link. Well, not the lower star here. I think I use black to indicate lower link. blue to indicate lower star. So let's look at the first figure here, the one on the left. The lower link here consists of this entire one cycle, this entire collection of edges that forms the cycle around the blue vertex. The lower star is essentially all the edges and triangles that are incident on the vertex at the center. So this is how the neighborhood of a maximum looks like. The function at all the neighbors is less than the value at the vertex. So in other words, the lower link is a cycle. It's a one cycle. And how do we characterize this lower link? We could compute its Betti numbers, for example. And what would be the Betti number be? The Betti 0 of this lower link of V is going to be 1, and the Betti 1 of the lower link is going to be also equal to 1. What happens for a saddle? As you can see here, well, before that, maybe let's look at the minimum. The minimum is characterized by the fact that all the neighbors have function value greater, so the lower link is empty, which means that Betti 0 is, for the lower link, is going to be 0. So which means that Betti 1 naturally is also 0, right? So I just write that down. Now for a saddle, what happens is that Betti 1 is 2. So you can infer this from our previous discussion for smooth functions. This holds for the case of piecewise linear functions as well. This was formally shown by Banchoff, but it is a fairly straightforward argument. Well, I'm sorry, Betti 0 is 2 and Betti 1 is 0. So remember that we are writing the Betti numbers of the lower link. So as we can see that the critical points are completely characterized by the Betti numbers or the topology of the lower link. The critical points may not be as nicely behaved in the case of piecewise linear functions. In fact, there can be other kinds of saddles, so-called monkey saddles, which do not fall under one of these three categories. So in fact, for a typical monkey saddle, the Betti 0 would be greater than 2. But these can also be handled in practice. For now, let's restrict our attention to the simple saddles. Let's see how this description and this characterization extends to 3D. So in 3D, again for a minimum, the lower link is empty, right? For a maximum on the right, the lower link is exactly equal to the link. So if we want to use Betti numbers to characterize, then the Betti 0 of the lower link is going to be 1. Betti 1 is going to be 0, and Betti 2 is also going to be 1, because there is a 2 cycle which is non-bounding. How about a saddle? In the case of, there are two kinds of saddles as we saw in the previous lecture. A one saddle, Morse index 1, will have two components of the lower link. It will have two components of the lower star as well, if that helps. So Betty 0 of the lower link is going to be 2, Betty 1 is 0. Whereas for a two saddle, the lower link looks like an annulus. So the Betty 0, the number of components is 1, and Betty 1 of the lower link is also 1, because there is a tunnel, a single tunnel. So just like we saw earlier, we could have monkey saddles or the equivalent of monkey saddles in 3D. So more generally, multi-saddles. These multi-saddles are characterized by the fact that their lower link has more than two components, or the lower link has two components, and in addition the lower link also has a non-zero Betty 1, such as what is shown here. So again, to begin with, we assume that such multi-saddles do not occur, and we proceed. And towards the end of this lecture, we'll see how to handle them in general. Right. To recap, the way we extended the notion of Morse function to piecewise linear functions was by looking at the lower link and computing its Betty numbers, and using these Betty numbers to characterize or to identify the Morse index. We made two assumptions. We assumed that the link could be partitioned into the lower link and the upper link. Well, the link is not truly partitioned. What we said is that the vertices in the link can be partitioned into the lower link and the upper link. So namely, given any vertex v, its neighbors are either lower or higher in terms of function value. So what this meant was that we had assumed that there are no flat regions. So f of x not equal to f of y for two distinct vertices xy. We also made the assumption that there are no multi-saddles. In practice, we do come across situations where the function has flat regions and the function has multi-saddles. In fact, this is quite common. An easy way to handle this is via this notion of perturbation. In practice, this perturbation turns out to be quite simple, but there is a strong theory that supports this. One way to handle the notion of flat regions is via the idea of simulation of simplicity. So I'm not going to describe the technique here. I would suffice to say that whenever we want to compare the function at two vertices, f of x and f of y, we ensure that we return only a less than or greater than by using the index of the vertex to break ties. So what this means is, if f of x equals f of y, then we use the index of the vertex in memory to decide who is greater and who is smaller. So this idea and the formalization of this idea is called simulation of simplicity, and it was introduced by Edelsbrunner and Muka. So if you search for simulation of simplicity, Edelsbrunner and Noka, you should be able to find the paper. The idea in practice, in terms of implementation, is quite easy, but there is very strong theory that supports this. The way we can handle multi-saddles is by splitting them into simpler saddles. I'll show an illustration for this. So here is a multi-saddle on the left. As you can see that this is not a simple saddle. The function is increasing and decreasing alternately 3 times, right? The way to break this into 2 simple saddles is by splitting the vertex into 2 and arbitrarily calling one of them as having greater function value than the other, and that's it. So the 2 vertices that you see on the right, both are simple saddles. You can convince yourself. So let's say that the vertex on the top here is greater, right? Has greater function value. Then you can convince yourself by looking at its neighborhood that it is a one saddle, and or rather here it's a saddle. There's only one type of saddle in two-dimensional for two-dimensional functions, and you can convince yourself that the other saddle is also a simple saddle. Such a split can be used to used in 3D as well. So a multi-saddle in 3D, such as the one we saw earlier, can be split into 2 simple saddles. One of them is a one saddle with 2 lower link components, as you can see. The split is shown here via this geodesic. So you can imagine that the vertex at the center is split, and the neighborhood of that vertex is split along this great circle, and the vertex that is on the upper part of that plane is the one saddle that you see on the left here. This is the one saddle. And there is another vertex which is the 2 saddle. So if you look at the neighborhood of the 2 saddle, you can see that it is an annulus. So what you see in blue here is the neighborhood or the lower link neighborhood. What remains are the regular points. So any point that is not critical is called a regular point. So of course the number of critical points is often much smaller. The number of regular points is much larger. So these are the more commonly occurring points. So similar to how we saw and characterized critical points using different notions, we can look at the regular points also along those viewpoints. So by looking at the gradient lines, so the gradient lines in the neighborhood of a regular point do not change. If you look at the isosurface as it passes the function value of a regular point, there is no change in topology. So the before and after picture looks very similar except for the change in the geometry. So in this case you have one component before the isosurface passes the regular point and one component afterwards. If you look at the lower link and use that to characterize, then for a regular point the lower link has one component and no holes. So Betty 0 is equal to 1, Betty 1, Betty 2 and so on are equal to 0. Right. Right. So with that, we have seen how we can characterize the critical points of a piecewise linear function using the ideas that we learned from Morse theory, which was originally introduced and developed for smooth functions whose critical points were non-degenerate. Let's conclude this discussion by going back to Euler characteristic that we have seen earlier. The Euler characteristic is a topological invariant. We saw that as well. It is also a shape invariant. It has been introduced and reintroduced in multiple disciplines. We already saw that the Euler characteristic is equal to the alternating sum of the k simplices. So what is true is that the Euler characteristic is also equal to the alternating sum of critical points. So the Euler characteristic chi is equal to the alternating sum of the number of I simplices S sub I. So S sub I here denotes the number of I simplices. You already saw that the Euler characteristic was equal to the alternating sum here of the I simplices. You saw that it was also equal to the alternating sum of the Betti numbers. What you see here now is that it is all this Euler characteristic can also be written as the alternating sum of the critical points C sub I, where C sub I denotes the number of critical points of Morse index I. So if you have a three-dimensional function, then this is equal to the number of minima, that is index 0, minus the number of 1 saddles, plus the number of 2 saddles, and minus the number of maxima, which is the number of critical points with index 3. We will not prove this in this lecture. We will wait until we introduce an algorithm for computing this notion of topological persistence, and then come back to this expression and see a proof. So the way the Euler characteristic is introduced here, or at least seeing these two expressions, one may think that the Euler characteristic depends on the simplicial complex or the Morse function. But you already know this is not true. You already have seen that the Euler characteristic is equal to the alternating sum of Betti numbers. So you know that it is a invariant and it's a property of the topological space. So as an exercise, you may want to try and compute the Euler characteristic of different topological spaces, either by computing their Betti numbers or by designing some Morse functions on them and computing the Euler characteristic using this formula you see here. So a sphere, for example, has Euler characteristic 2. So you can design a function which has a single minimum and a single maximum. So when I say a sphere, I mean here a sphere in any dimension. But you could take, for example, the two-dimensional sphere, and show an example of a Morse function. Similarly, the torus has Euler characteristic 0. The double torus has Euler characteristic -2, and so on. So I have also introduced these three specific topological spaces here for a reason. These are all surfaces. These are all two manifolds. So it turns out that the Euler characteristic can characterize the two manifolds up to orientation. So these surfaces are what are called orientable surfaces. I think you have seen the notion of orientation also. So when I take orientable two manifolds, so all two-dimensional manifolds that are orientable, then I know that they are fully characterized by the Euler characteristic. So what that means is that if you give me two different topological spaces, you tell me that they are orientable to manifolds, then I can identify which two manifold you have given me by just computing the Euler characteristic. So this essentially says that the Euler characteristic is, so what I'm saying here is that the Euler characteristic here is equivalent to this stronger notion of homeomorphism that we have seen. In fact, it happens to be stronger than that, but we'll stop here. So the Euler characteristic is able to classify the orientable two manifolds up to homeomorphism. So this is a classic result in topology. I'm just mentioning it here for as side interest. So this is called the surface classification theorem. Surface classification theorem. So let's conclude. So what we have seen in the in these lectures on Morse functions, we have seen the notion of a Morse function. We have seen that a Morse function is a smooth function that has no degenerate critical points. We saw that almost all the smooth functions are Morse, in the sense that you can perturb any function, any smooth function, and make it a Morse function. We saw that the Morse function has some very nice properties in the neighborhood of a critical point, namely that it can be written as a quadratic function. We use this to introduce the notion of Morse index. It is the number of negative eigenvalues of the Hessian, or the number of principal directions of instability in the neighborhood. We extended these ideas to piecewise linear functions so that they are of practical use in order to study scientific data. So in particular, we saw how the lower link structure and the Betti numbers of the lower link completely classifies the critical points. So a point to note here is that the critical points helped us also capture exactly where the topology of the isosurface changes. So if you are given a scalar function f, and you are, let's say you are looking at its isosurface, right? So which is the pre-image of any scalar value c, and you look at how the topology of this surface changes as you keep increasing c from negative infinity to positive infinity. The critical points are exactly where the topology of this isosurface changes in terms of number of connected components, in terms of genus, and so on. So there is a relationship between critical points and the topology of the isosurface. There is also a good connection between the critical points of a Morse function f and the topology of the domain. One way to see this is via the Euler characteristic. We saw that the Euler characteristic can be written either as an alternating sum of critical points or as alternating sum of Betti numbers. So there is clearly a relationship between critical points and the topology of the domain. So with that thought, we'll end this discussion on Morse functions. And this should be sufficient background for us to talk about specific topological structures that have been introduced to study scientific data.